one application to the um, dynamic fluid, we consider a large tank. We have large tank filled with water at a height capital H equals to 3 meters. So when I say we have a large tank, it means we have a large cross-sectional area. Where here we have A1. A1 is very large. The system is provided with a small orifice where we have the outlet and we have the flow of the fluid. So here we have a dynamic configuration where we have a flow of fluid, uh, and I ask you to find the speed of fluid at the point 2, at the outlet of the orifice. So we can say here, I ask you to find V at the point 2, and this point is located at the outlet of the system. Okay, don't forget we have A1 is very large. You know, in the case of dynamic system, we have two equations. We have Bernoulli equation and the continuity equation. First of all, you know the continuity equation A1 V1 equals to A2 V2, and this value equals to the volumic rate of flow QV is constant at any point inside the system. We can choose any point. In this case, with this example, I advise you to take one point at the top of the system. Why? Because I know its value of P. P applied at this point equals to P0. Okay? And we can take as a point 2, you know the point 2 also is in contact with the external pressure. We have here also P0 applied as a point 2. So at any point in contact with the external atmosphere, we can take P equals to P0, like the point 1 and the point 2. Okay? So this system and this configuration, uh, it's similar to this configuration, as we have a large tube and a small tube. And I take one point here and one point here. You can calculate P at this point P1 and P at the point P2. We can calculate H, we can calculate V, and we can apply Bernoulli equation to this configuration. Okay, you know, we talked about this point before. Now we have to apply the same configuration for a large tank with a small orifice. Okay, so Bernoulli equation equals to P1 plus rho GH1 plus rho divided by 2 V1 square equals to P2 plus rho GH2 plus rho divided by 2 V2 square. Let me write the definition of each one. You know, P1 equals to P2 equals to PO. So we can eliminate P1 here and P2. What about the height? We have to take the lowest, the origin as the lowest point. We can put here the origin. So we have H1, which is equal to capital H, and H2 equals to 0. We can write here H1 equals to the capital H equals to 3 meter, and we have H2 equals to O. We can eliminate H2. Okay? We can also eliminate the density. Here we have a density, density, and density. Let me explain one point in the case of a large tank. You know, here we have the continuity equation A1 V1 equals to A2 V2. Only for a large A1, you can say here V1 equals to A2 divided by A1 times V2. If A1 is very large, so V1 is approximately negligible. Okay? So we can eliminate V1 only in the case of a large tank. So we can eliminate V1. But you have to say that in the case of a large tank, you can neglect V1. Finally, we can calculate V2, which is equal to radical 2GH. H, I mean capital H. Okay? So we can write here V2 equals to radical 2GH. We have 2 times 9.8 times 3. It's about radical 60 m per second. I tell you something. For any system, for any large system, like this example, I give you, for example, this system, we have a large tank, and here the velocity at the outlet, it can be at this point, or we can have some installation for configuration like this. Okay. So in this case, the outlet will be at this point. So if we have here point 1 and here we have point 2 at the outlet, you can say V 2 equals to radical 2G times the height between the in and the out. You know, here we have the in and here we have the out. The h of the height between them, okay, we can say like this. This is h. You can say h, or you can say small h. H between 1 and 2. But you have to precise that A1 is very large, and you have to say also V2 equals to A2, no, V1 equals to A2 divided by A1 times V2. In this case, V1 equals to 0. Okay? For any problem, you can write directly this result without writing Bernoulli equation and without all these calculation. Okay, the second point, I ask you to find the volumic rate of flow. I want to find QV. You know, QV is constant at any point inside the water. You can say QV equals to A1 V1 equals to A2 V2 equals to A2 V2. So we can calculate Q from A2 V2 because we have the diameter of the orifice. We can say here QV equals to pi divided by diameter divided by 2 square times V2 radical 60. Okay. Like this, we can calculate QV. You know, QV is a volume per unit time. You must have volume per unit time. It means m cube per second. We calculate the answer. You know, pi equals to 3.0 14. D equals to 10 times 10 power minus 3 divided by 2 square times radical 60, the unit, and the answer will be meter cube divided by second. Okay, let me calculate. Equals to 0.608. This is the value of the quantity. Is the volume per unit second. We can say the rate of flow, the volumic rate of flow.